So, guys, welcome to the poster session, the virtual poster session of the workshop. My name is David Portugal. I will be moderating this session. We will have two papers to be presented. So the first one is vegetation classification using DeepLab v3 Plus and YOLO v5. And it's going to be presented by Professor António Paulo Coimbra from the University of Coimbra. And so, Professor, the microphone is yours. You can start. Thank you.
Okay, thank you. I will share the screen. Okay. Are you already seeing my screen? Okay. Good afternoon, everybody. I am Paul Coimbra, and I am presenting the paper vegetation classification using DeepLab v3 Plus and YOLO v5. This is a work done mainly by Paulo Mendes, which is a PhD student within the Institute of System and Robotics, University of Coimbra, Portugal. This work has been done in the scope of the Safe Forest project, and its motivation is mainly the prevention of forest fires. Forest fires are increasing in the world, and they imply a loss, great loss in property and sometimes human lives. And so within the scope of this project, we intend to make some prevention of forest fire by having the vegetation cleaned using UGV. So to do that, we need to make vegetation detection, its classification and localization, so we can have an autonomous navigation and local mapping for the cleaning mission. And this has to be done in real time. So the contribution is mainly the comparison of two models to classify vegetation to be cleaned. The DeepLab v3 Plus and YOLO v5. With the DeepLab, which is a recent model, we have formed semantic image segmentation, where the goal is to assign semantic labels to every picture in the output image, like in this one. It is open source by Google. The YOLO v5 is a little more recent, and in our case, we are predicting with bounding boxes and also class labels. And we are using, in this case, our own data set. So for the semantic vegetation segmentation using DeepLab, it will use an already trained model trained with the Cityscapes dataset, pre-trained with the mobile net backbone. And it was used with a set of images took in a forest nearby our department. The results with the DeepLab, these are at the top, these are the input images. And here we have the output, the segmentation, the vegetation segmentation. You can see here that the segmentation was well performed, with a car being detected, with some road pavements, the pole, illumination pole, And when we have hard lighting, we still have a positive identification of vegetation. But when we have cut vegetation, we have some misinterpretation results. So here the results are not so good when we have cut vegetation. When using the YOLO V5 model, we have trained this model with a data set of 200 images, 150 for training, 30 for validation, and 20 for testing. And these images were also took from a forest nearby our department. And it was the pictures were labeled with 5 classes: live vegetation, grass, cut vegetation, tree trunk, and dead vegetation. And the training was done with 1,000 epochs for each, and using Google Colab. These are the metrics during the training, and the mean average precision and 0.5 intersection over union were were about 76%, and so the training was successful. And these are the results with the same set of images. And here we see the segmentation, the bounding boxes. And when there is direct light and shadows, there is also still an identification of vegetation and tree trunks. And when we got the cut vegetation, there was some success, success in identifying the cut vegetation. So this model performed better in this aspect than the previous one. About the computation time, with the YOLO V5, we succeeded in having model runs 25 times faster. So we reach real-time processing capability with the YOLO V5 model. So the conclusions. We have made the semantic segmentation using the 2 models. This is done to clean forest fuel to prevent fires by an unmanned ground vehicle. And using the DeepLab pre-trained model, the results were effective in detecting green vegetation, but in detecting dry or cut vegetation, there were some misclassifications. Using the YOLO V5 model, the results were effective also for classification of vegetation, and with the YOLO V5 model, the performance was better in detecting, differentiating between live and dead and dry or cut vegetation. So by comparison these 2 models, the YOLO V5 model looks better to be used for this usual mission. And so it will be used for the detection, classification, and localization of local vegetation in a forest environment. The results show real-time processing capabilities, and so we believe this is the way that we should proceed in our project for cleaning forest environments using autonomous robots. And 6 minutes presentation. This is it.
Thank you, Professor Paulo Coimbra.
It's not moving on. Okay, thank you very much.
Thank you very much for the interesting presentation. So I'm now asking the audience if there are any questions that you would like to pose.
Yes, could. Is it okay if I ask a question?
Yeah, of course.
Yes,
go ahead.
Okay, I was a little bit confused on the data set. So you annotated 200 images, but used pre-weight from Cityscape. How were the 200 images annotated? And is it possible to increase the amount based on just the sheer amount that you have?
Trying to, this is a little slow. Put the slides. So with the YOLO V5 model, we have used the 200 images. We can increase this data set, yes. Namely to use images from other forests, not only this one. On the regarding the DeepLab model, this was used using pre-trained model, a pre-trained model. So we didn't use our data set to train this model. I don't know if I answer your question.
A little bit, and I would like to understand why the sample chosen was 200 images. Was it a limitation on how to annotate, or was it just a number you believed it was enough for avoiding overfitting?
Well, we are limited by the time, and because the model ran well, we didn't look to increase the number of images. The idea now is to use images from other forests and check if it works well also, and if we need to increase more the number of images. Different forests with different species might pose different issues in identifying vegetation, because the ground vegetation is different from forest to forest, and so this is a kind of something that we have to check. If with different forests, with different types of grass and ground vegetation, if detection still goes well or not.
Okay, thank you very much.
You're welcome.
Thank you, Eduardo. Professor, I also have a question, which is, in which applications do you feel that YOLO V5 would be better in classifying vegetation, as, for instance, comparing against semantic segmentation?
We are still working on this matter, so I still don't have, let's say, a final answer to that question. I expect that using the YOLO V5, things run in a more fast way, so we have more real-time processing, and the idea is to have local navigation. So it is important, while the UGV machine is being cut the vegetation, to differentiate between the already cut vegetation and the one that we need to still to cut. So in order to do not leave behind uncut vegetation and to not try to cut the same vegetation twice. So we hope, and we are working on that, that with the YOLO V5, we can achieve this kind of differentiation and localization of the cut and uncut vegetation, while the UGV is in the cutting mission.
Okay, thank you very much. Any further questions? Okay, so I would move on then to Dominic Bittner. He's here with us, so he's going to present a second paper with title Generating Synthetic Multispectral Images for Semantic Segmentation in Forestry Applications. Dominic was a visiting researcher at Nottingham-Trent University and the University of Coimbra. He's originally from the Technical University of Regensburg, right, Dominic? And well, he's going to present our paper on the semantic segmentation. So go ahead.
Hi guys, are you already able to see my screen?
Yes.
Yeah, okay. Hey, my name is Dominic Bittner, and I would like to talk with you about generating synthetic multispectral images for semantic segmentation in forestry applications. The co-authors are João Ferreira, Maria Andrade, Jordan Bird, and David Portugal. Okay. Yeah. First of all, we need to define what semantic segmentation in forestry robotics is. To be able to operate in forestry applications, autonomous robots must be able to perceive the surrounding environment and classify entities according to their task relevance. For example, semantic segmentation, which is in turn the classification of individual pixels. These are supervised models using pre-annotated datasets. But when these models reach their performance limits due to the limited amount of annotated data, data augmentation can extend these datasets to improve the original training. In this case, classes relate to a forest landscaping mission for fire prevention, where live flammable material is the material to remove, trunks and canopies are the plantations to protect, and humans and animals are the wildlife and potential co-workers to avoid for safe operations. Multispectral images, which are coming from the camera mounted on the Ranger, are expected to improve perceptual capabilities when compared to RGB imaging because of specialized filters, in that case the near-infrared channels, which detect chlorophyll and can therefore enhance the plant detection. For example, by using vegetation indices or deep learning methods for semantic segmentation. To augment data, generative adversarial networks or short GANs could be used. These are the composition of two competing networks which are trained simultaneously by an adversarial process to generate new data, where the generator G captures the data distribution without direct access to real data from X, while the discriminator D estimates the probability a sample comes from the training data X or from the generator G. In that case, the generator learns how to replicate the given data from X by interacting with the discriminator D. By feeding random noise Z and potentially other inputs into generator G, the GAN is capable of producing a wide variety of data derived from the target distribution for data augmentation. A specific type of GANs are image translation GANs, which are the conversion of an input image XA from a source domain A to an output YB into target domain B, with the intrinsic source content preserved and the extrinsic target style transferred. If you refer to the previous figure about GANs, this image-to-image translation shown in that figure is constrained or conditional, since it receives a label image X, which can be an outline or pixel-wise annotation. These two figures show a brief illustration of the process. The input image in both figures are separated into their individual components for translation and later to be combined again with synthetically generated parts. In the process, the GAN learns the correlation between original multispectral images and their corresponding near channels. The generator model can then be transferred to translate RGB images into synthetic multispectral images for data augmentation purposes. The following methods were implemented for image-to-image translation. Pix-to-Pix GAN is a conditional pixel-to-pixel translation method, while Pix-to-Pix HD GAN is the first extension with a high resolution and photorealistic image generation. GALGAN is in turn the extension of Pix-to-Pix HD GAN, where more accurate networks for high precision image generation to avoid washing away the information contained in the semantic segmentations are used. As you can see in the preliminary results, the image translation done by Pix-to-Pix, Pix-to-Pix HD, and GALGAN is not distinguishable to the ground truth and the input multispectral image. Further, the semantic segmentation using translated images from Pix-to-Pix, Pix-to-Pix HD, and GALGAN achieve the same results based on visual inspection as in the baseline training or compared to the ground truth annotated by human experts. In the quantities evaluation, the F1 score, intersection over union, and recall are used as metrics to measure the accuracy of a classifier model, or in that case, a semantic segmentation model. Besides them, inception score and Frisell inception distance, or short IS or FID, are chosen as common metrics to evaluate the generated images on themselves. The percentage column in the left table provides the ratio of the parameter means of each model as a percentage of the baseline in the first row parameter mean. Besides these numerical evaluations, it should also be considered whether a solution has the potential to improve the images or not, the image generation or not. The results in both tables show marginal differences between each method. As a conclusion, in general, all tested methods provide satisfactory results for the pre-established target. Based on the evaluation results, GALGAN marginally offers the most appropriate solution for future use in synthetic multispectral image sample generation for data augmentation. Future work will focus on data augmentation for semantic segmentation by generating synthetic multispectral images from RGB images taken from a photorealistic forestry simulator, which allows the capability of generating an unlimited amount of training images with ground truth labeling for data augmentation. Thank you for your attention, and if you have any questions, just let me know. I'm happy to answer.
Thank you very much, Dominic. You were able to do it on time. So I would now ask the audience if you have any questions, please shoot away.
With a bit of rush.
Yeah, I have one question. This is my first contact with this technique. I was wondering if there is, if you expect any negative effect of direct sunlight images and in the process, if it would be resistant to this effect or not, to direct sunlight and shadows.
First of all, I need to say in that respect that each part which is in the training images, sure, the GAN network on itself learns as well. So it depends on what you feed into the network. So if you have for example, bad samples with sunlight or sun reflects in there, your GAN also learns this bias, for example. But to avoid this effect, you can also use first classification of the images to detect the sunlight, so that you can, for example, just use the images which are without sunlight effect, since as you just think of, if a GAN or that networks is already trained with that samples, it also replicates them. So you cannot remove that effect, but if you classify these images already before the training, you can avoid that effect. So if you have a huge bias in your data set, you can already remove it, or it is suggested to remove the bias already before your training of the GAN to get better results from your GAN training. I hope that answered your question.
Yeah, thank you.
You're welcome.
Any further questions? I also would like to congratulate Dominic, because he recently graduated from his bachelor's in Germany after his visiting period in Portugal.
Thank you.
We're all very proud of you.
Thank you. It was a pleasure. Or is still a pleasure working with you.
Yeah, of course. And well, if there aren't any further questions, we would end this virtual poster session, and let's wait for the guys at the conference, at the workshop, to synchronize back with them again. Okay, so we'll just keep ourselves here steadily in the Zoom session. Okay.
Okay.
Thank you for moderating.
Thank you all, guys.